Thank you, Mariam, for the invitation. I'm glad to be back. So today I'm going to talk about the eigenmatrix for unstructured sparse recovery. So let me just tell you what the problem is. So the problem is the so-called unstructured sparse recovery problem. So here's the setup. So X in this part we denote a parameter space, and so we want to discover essentially the points in the space. Okay. So S is the so-called sampling space. These are the points where we actually can collect samples. So another important thing is this G, which is the kernel. The kernel takes two variables, S and X. So it tells you that what the sampling point S feels about the parameter space X. Okay, and in this talk we require that the kernel itself is analytic in X. You can think about that. It does not require anything strong in S, but in space X it has to be analytic. Now, what do we mean by the sparse recovery problem? So the problem is that we want to recover this function fx, which is defined over the parameter space. And it is sparse, so therefore it has a bunch of deltas centered at the location x1, x2, all the way to x, nx. There are nx of them. So nx's will be small. Think about there's only 5 or 6 different spikes. And each of the spikes will have a weight which is called a wk. Okay, so it's the sparse function we want to recover. And we don't get to see this function, but somehow we get to obtain some kind of information about this function through this kernel G. So we're able to have access to this function us, which is the integral of capital X of G of this kernel multiplied with this unknown function. So because the unknown function itself is very simple, it's a bunch of deltas, so we can simply write this as a simple sum. It's a sum of k from 1 to the number of spikes and G at the sampling location xk times wk. And again, wk are the weights. So, but unfortunately, we don't get to see this function at this u function at all the locations, but we actually can only observe it at a bunch of unstructured points. So unstructured will become clear. Why do I want to emphasize unstructured will become clear in a second. But these SJs are, you can think about them to be a bunch of points someone gives to you. You don't have the chance to change them. You don't have the right to choose them. And at these points SJ, we can observe uj, these quantities, which are approximation to the of this function u at sj. So in the ideal case, the uj will be just equal to usj. But unfortunately, if you have noise, I mean, the signal gets polluted a little bit, so you only get a noisy observation. But for the time being, you can just think about it to be perfectly equal to the function value at sj. Now, the task of this unstructured sparse recovery problem is to want to recover the locations xk of our unknown signal and also the weights wk of the unknown signal. Okay, so again, I want to emphasize that the problem is sparse. It's unstructured. And also what we want to recover is xk and wk. Now, it's probably not a good idea to present such an abstract problem right from the beginning. So let me just show you 5 examples. And these are actually quite common. So in the first example, in my community, it's called rational approximation. So the idea is the following. So x, the parameter set is going to be an open setting in complex plane. So in the simplest case, you can think about it as a disk. Or maybe it's a lower half plane, or maybe it's any kind of nice open set. Okay. So and the S, the sampling locations are going to be actually the complement of this capital X. So you can think about this is a little bit distance away. All these. So the red point, yeah, S is right here. Okay. And now the kernel is very simple. It's just 1 over x minus x. So you have 2 complex number s minus x. You take the reciprocal. That's my kernel. And what are the quantities I want to discover? We want to discover these red points, which is my location xk. And also at each of the red points, there's also associated weight, which I didn't draw, is the wk. These are the things what I want to recover. And what are the sampling locations? Sampling location is sj. These are the yellow points here. Okay, so I want to know this function, and at each of the sampling location, I have uj, which is given by the sum over this kernel multiplied by wk. So I got to observe the function value u at these yellow points. I want to figure out what are the location of these red points and what are the weights of it. So this is problem is called rational approximation. There's another special rational approximation problem which is so important in quantum mechanics and quantum many-body system, so that people give it a special name. It's called spectral density approximation estimation. So in this case, x is going to be an interval of the real line. So assume that it's from -b to b, and s, instead of having the whole complement, is actually only going to be restricted on the imaginary axis. Okay, and the kernel is the same, is 1 over s minus x. And xk at the unknown locations are the red dots. It's corresponding to excitation energies in quantum mechanics. And wk is corresponding to the weight of these energies. And Sj has a special name, and these are equally spaced points on the imaginary axis. These are called Matsubara grid. It's equals to the 2j minus 1 times pi over beta and times this I, which is imaginary on the imaginary axis. And this beta has a meaning of called inverse temperature, and this is a standard notation using physics. And now, what we get to do is that we get to observe this function u at these points on the imaginary axis. Maybe typically have a dozen of them, maybe 100 of them. And what you want to do, you want to figure out these red locations on the potential energy spectrum, and also figure out the weights. The third problem is it's what I call the Fourier inversion problem. So here x is, you can think about as an interval. X typically stands for space, but in this case, x you can think about this as a frequency. So you can think about this as from -1 to 1, okay? And the s is the real axis. And the kernel itself is actually corresponding to different Fourier bases. And they are parameterized by x, which is corresponding to the frequency. When x is large, you have high frequency. When x is low, you have low frequency. Okay? So essentially, you have a bunch of for example, in this picture, I have 2 red dots. So this corresponds to high frequency, so you see it oscillate quite a bit. And this corresponds low frequency, is oscillate only a little. Right? And each of them has a weight, which is W1, W2. And when you add them together, you get a signal, which is essentially the sparse in the Fourier domain. And you get to sample these locations, Sj down here, these yellow points. And what you want to do is that from these observations, and most of cases noisy observations of these the signal at these Sj locations, what you want to do is you want to figure out these xk, my frequencies, and also the wk, which associated with these frequencies. Okay. The next problem is related to Laplace transform. So here, x, my parameter space, is corresponding to a positive interval from 0 to a. So 0 corresponding to no decay, a corresponding to large decay. And x is corresponding to my positive real axis. The basis function, or the kernel I have, is exponential minus xx. So when x is large, you see that it has rapid decay. No, sorry, is that correct? Or maybe but anyway, one of them is gonna, here, big A is down there. So when A is large, so you actually have very fast decay. It's an exponential kernel. When x is small, you have slow decay. So the signal is actually essentially is the linear combination of a few these decay exponential modes, and observe at these yellow locations. And then from the combined signal, I want to figure out what are the decaying rate for each of the mode. And I also want to figure out what is the weight, this wk's. Okay. Finally, this is an example called a sparse deconvolution problem. So this is the problem is probably the easiest problem among them, but can also be casted in this way. Is that suppose I have a parameter space is between the interval a and b, and s is the real axis. Now the kernel itself is any translation invariant kernel. For example, I'm giving this kernel look like a Cauchy kind of kernel here, 1 over 1 plus gamma, which is the constant of s minus x. Okay, so here I'm drawing the shape of this kernel. You see that each of this is roughly look like a bump with this algebraic decay, and the center location of this is going to center at x. So the signal you obtain is actually a linear combination of several of these bumps, which indexed by these red points with appropriate weight. And you'll get observe them on a few these yellow points, which again are unstructured. And what you want to do is that you want to figure out the weights and also the locations. Okay. Now, so you see that I give you a couple of examples, and by now hopefully I convince you that this is a quite general problem. And in fact, there are many papers written to address each of these examples. So for example, rational approximation is a well-known problem with long history in applied math and also computational physics. Here I'm listing some of the recent papers that recent methods has been proposed for solving rational approximation problem. So RK-fit and barycentric interpolation, AAA methods, and these are some of the methods people use quite a lot. Spectral function approximation, this related to Matsubara grid, has a long history in physics, and I mean, it still is a hard problem because it's quite ill-posed. So many methods have been proposed for that, including particular approximation, maximum entropy methods, stochastic analytic continuation, and recently there's quite a few. There's a surge of attention again in this field, and there's quite a few papers that have been published in recent years. Among them, Fourier inversion is probably the most well-known method problem because the Fourier signal is so universal; it appears everywhere. So in the case when actually you have equally spaced samples, and also your frequency x actually come from an also equally spaced grid, and this falls into the category of compressive sensing, which received a lot of attention in signal processing in recent years. And there's a vast literature on using L1 methods to solving relaxation methods to solving this Fourier inversion problem. But when you move away from this Cartesian structure, either in the frequency space or in the sampling space, this becomes the so-called line spectral estimation problem, which has been well known in electrical engineering for many, many years. There's also sometimes called a super resolution problem. And there's this famous paper by Donahoe in '92, which studied the resolution limit of those kind of problems and the impact of noise. So many methods has been proposed for that. Among them, there's this so-called Prony type of methods, which I will go into detail in a second. Is actually and different variations of the Prony methods have been invented to study line spectral optimization problem. Until this day, the theoretical analysis of the Prony type methods is also a very active field. Okay. And also, there's quite a lot of optimization problem because you can naturally cast this into optimization problem and solve it. Now, the Laplace inversion problem is trying to estimate the decay of these exponential modes, and in this way is actually a very hard problem because you know that these kernels decay very rapidly. Any noise is actually going to result in instability in the reconstruction. So when you have random access, meaning that you can sample the signal, resulting signal anywhere you want, this becomes slightly easier. There's quite a big literature on that. But on the other hand, in our case, it's much harder because we're given the location of the samples. We don't get to choose where we want to sample. So the problem is much harder. So the sparse deconvolution problem also appear quite often in the literature. And in the uniform case, by using a Fourier transform, it goes back to this Fourier inversion problem, super resolution. But for the unstructured case, it's less studied. This is a partial list of the recent work has been devoted into this field, but I'm sure there are papers which I missed. So in this talk, I will try to present a general approach for solving these unstructured sparse unstructured problem, recovery problem, so the talk is going to consist of three parts. The first part, I'm going to go back and visit one of the old methods called Prony's method, which is a very beautiful method, but solving only a very special case. And we'll try to go into details what is Prony methods and try to understand what is really important in the Prony method. And then I will try to use ideas from the Prony's method and try to generalize to get this approach, which in the title is called eigenmatrix approach, and which allow us to address all the 5 cases that we have I have listed before. Then finally, I will present some numerical methods. Okay, so this is the outline of the talk. So any questions before I go into the more technical details? Okay. All right. So what is the Prony methods? So Prony methods is actually a method to solve this sparse recovery problem, but in a very, very special case. So it requires a special. So my parameter space, it doesn't really need to be 0, 1, but it's convenient to set it to be 0, 1. My parameter space is 0, 1. And the kernel for this sparse recovery problem is actually the Fourier kernel. Okay, so the nicest kernel that you can think about. And the sampling location is actually going to be a uniform grid. Okay, so our problem is different. The problem we want to address is that the kernel has to be general, and also this location, the sampling location, is actually unstructured. But Prony is addressing a special case for a special grid. And plugging this kernel into my U function, you see that the sample we get is exponential. The sum of these exponentials at the frequency xk, the unknown frequencies multiply with the weight wk. Okay, this is the samples we obtain. Now, the Prony method essentially does start with the following. There are many ways to formulate the Prony method, but I'm gonna try to explain the Prony's method in a way that connects well with the new approach. So it might be a little bit different from what you saw before. So the first step of the Prony method is to define this this G function, is this G vector, which is actually it's a function because it's parameterized by my parameter X. So because so we don't really need to know the sample for all the integers, but let's assume for convenience for the presentation, let's assume that we have the samples for all the integer locations. So Gx essentially is evaluating this kernel, which is which our Fourier kernel, with a frequency x at all the integer grid, and I concatenated them to be a very long, infinite long vector. Okay, this is my Gx. So this both G will always stand for a vector. Now the second thing the Prony methods introduce is this so-called shifting matrix. So the shifting matrix is very simple. It's essentially is that to take any vector and shift everything up by one slot. So essentially the matrix representation of M is on the diagonal 0, and here is 1, everywhere else is 0. Okay, shift up. So if you apply this M, the matrix, to a vector V, and you take a look at the J's location, it's going to be the J plus 1 location of the original matrix. You just shift the vector by one slot. Now, the key observation is that if I apply this M matrix to my G vector, what you get is that e to the 2 pi I x times G. This is very simple because you shift one slot, because this is a plane wave, so therefore every time you compare with the next slot, right, you gain a factor of 2 pi I x. Okay. Now, equivalently, if you allow me to write in the matrix form, this is n minus e to the 2 pi I x times identity applied to my G vector is going to be 0. Now, if you write this formula down, spell out all the details, this shift matrix, shift this vector, you get the next location, and you apply this operator to this harmonic wave, you get 0. Why this is important? The reason why this is important is that if you take a look at each of the mode xk, right, you apply the corresponding m minus e to the 2 pi I x k I matrix, you're going to kill it. Now, suppose I don't know about my xi, x1, or x2 locations, but I assume I know, right? Then each of them actually commute. This m minus e to the 2 pi x I matrix commute. Why? Because they only involve two matrices, m and identity. M commute with m itself. Anything commutes with identity. So therefore, these matrices commute, right? So therefore, if I multiply all these matrices together, one of them will be my xk. So therefore, it will automatically kill this vector xk, gxk. Okay. Now, why is this useful? The reason is now what I can do is I can take my data uj and concatenate uj into a very long vector. Recall that uj is what? uj is a combination of all these harmonic waves. So therefore, uj is actually equal to the sum of all these gxk with a weighted wk, right? Now, this operator now, it's independent of xk now because I multiply over all the possible xk. So it becomes an object which does not depend on any individual xk. So therefore, this object will kill each of the xk, gxk. So therefore, it will kill its linear combination, so it will kill u. Okay. Now, but if you take a look at here, so I have the product of these operators. So therefore, I mean, we can multiply them out. It becomes a polynomial of this matrix M, this shifting matrix, right? I write down this polynomial down. I don't know it, but because it's an nx degree polynomial, so therefore it has coefficients p0, p1, p2, all the way to p and x. Okay. So therefore, using this form, this polynomial form, and this equation here becomes p0i, p1n, blah, 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 multiply u is equal to 0. Now, each of them is a matrix. So therefore, I can apply the operator to the matrix first, and then do the linear combination with different p coefficients. And that still give me 0, right? So this is just doing a sum in two different ways. Either you apply the sum the matrix first, or you apply, sorry, I'm running out of battery. Okay. So either I'm doing sum the matrix and then apply the vector, or take each individual matrix, apply to the vector, and then the sum. Okay, so it's. Now I'm introducing this notation P here, where this vector P is actually a concatenation of all these coefficients. Now, if you take a look at what is this matrix? Well, the first column is just my uj data, right, that I received. The second column is going to be shift or uj, so it's shift up about one slot. The next one shift up by one slot, and so on and so forth. So this is a special case of the so-called Hankel matrix, okay, where the matrix value on these anti-diagonals are exactly the same. So in most of the presentation about the Prony's method, this is where you start. But somehow I feel like it's much more important to focus on this shifting matrix, which as you will see. Now, because we have this Hankel matrix applied to P is equal to 0, so therefore, what we can do is that P, the vector P, which is nx plus one dimension, is actually living the null space of this matrix, right? So therefore, I can take this matrix, I can try to identify its null space. So from this here, you can see that in fact I don't need an infinite long vector, because as long as my matrix is tall skinny, I'll be able to recover my null space in a quite robust way. So I don't really need all the integer grid values. Essentially I only need 2nx plus 1 of them. That would be sufficient. Now, once I recover this P vector, I'll be able to form back this polynomial, which Px is equal to P0 plus P1x, P2x, so on and so forth. And now recall from the previous slide, what is the relationship between this polynomial and this e to the 2 pi I? These are actually the roots of this polynomial, right? So therefore, if I can figure out the coefficient of this polynomial from the null space, then by finding the roots of this polynomial, I will be able to recover e to the 2 pi I xk. Okay? Now in this Fourier problem, xk is actually I restrict to 0, 1, but in fact, everything important is in fact encoded in this complex space. So therefore, we don't even need to recover xk itself. Once we have the xk, what do we need to do? We're going to plug it back into this formula for uj, right? And once xk is known, and this part is known, this whole thing becomes a linear system for wk. So therefore, I can solve a linear system or solve least square problem to figure out this wk roots. And then I'm done. So this is the case where I assume there's no noise, right? Once you have noise, things become more complicated. So you will see that the locations xk will have some error in it. The weight of wk will also have some error in it. Typically, what people do is that people use what we obtained up to this point as initial guess, and then solve a post-processing optimization problem. And that will allow yourself to improve the results a bit. Okay. So, but we don't need to worry too much about it. So this up to this point is the main idea of the Prony's method. Is the idea of the method clear, everyone? Yes, sure.
So here you calibrate every entry by 1 unit. How about the last entry?
Oh no, it's right. It's infinite matrix. It's d by d. It's infinite.
Oh,
no, it's an infinite matrix. Sorry, yeah.
Oh, I see.
I work with infinite non vector during the presentation. Okay. Good question. Okay. Now, but the Prony method has limitations for our purposes, because in Prony method you work with a Fourier kernel, which is a very special form, and also your grid is a uniform grid, right? There's all the SJ that location, integer location J's. So these two features are actually very important to give our shifted matrix, right? Because if you see that if the kernel itself is not Fourier, you don't have translation invariance, this is gone. If your grid is not uniform, you don't have Fourier translation invariance, this is gone, right? The reason why we have the shifted matrix is because everything is translation invariant. Without translation invariance, it's gone. But the problem we care about is that we want to care about the general kernel. There's no translation invariance in general. And also, we care about unstructured grid samples. So therefore, the problem is much tougher. Okay. So what do we do? So this is the second part, the eigenmatrix. Okay, so the idea is very simple. So in the Prony's method, we notice that the shifting matrix M is actually playing a huge role here, right? Essentially, this will give us a Hankel matrix. From the Hankel matrix, you have the null space. From null space, you have the polynomial. From the polynomial, you have the roots. And from the roots, you have the weights, right? This is the logical sequence. So from that level, it's really turned the nonlinear inverse problem, the unstructured of the recovery problem, to an algebraic problem, which is really root finding. Okay, so to something that you learn in the first algebraic class, maybe in high school. Now, for general G kernel and for the general sample SJs, what we want to do is that we want to do the same thing, but instead we don't have this n matrix, God-given n matrix, shifting matrix given to us. So we have to build this matrix ourselves. The way to do it is the following. I'm going to also construct the same vector G, which is correspondent for every x. My parameter is my kernel evaluated at all the grid points. Okay, so I can collect it. Now, because I don't have infinite data, so therefore this is the finite size vector, which depends on how many samples I have. This is size ns vector. It could be real, it could be complex, depending on the problem. Now, what we want to do is that we want to record that what's important about the shifting matrix. The shifting matrix is really essentially, you see, the most important formula is right here. It's really take this vector, it's going to give you an eigenvalue, which actually encoding my parameter. Okay, so we want to do the same thing. This is what I mean by turning this optimization problem, non-inverse problem, into an algebraic problem. So what we want to do is that we want to design a matrix M such that when you apply to this G vector, it's actually going to give you an eigenvalue x and also give this vector back. Okay, so the turning this vector into an eigenvalue. But now, unfortunately, we cannot do that for all the points because the matrix, we only have an ns data point. So the matrix size is ns by ns. So it has at the most ns eigenvalues. So but on the other hand, the parameter I can have is from an open set. I have an uncountable number of them, right? So therefore, I cannot expect this to be equality. I can only expect this to be approximation. Okay, but I'm a numerical analyst and I'm okay with that. So let's just go ahead. So this matrix that we want to construct is called eigenmatrix, and this I will show you a very simple procedure how to construct. Okay. So the matrix will satisfy this criteria. So I will consider two cases. The first case is that X is a complex domain. This is corresponding. So the first case X is a complex, and the second case I'm going to consider is X is an interval in the real space. Okay. So furthermore, I'll try to explain things in the simpler setting where my X itself not only is in the complex domain, it's also the unit disk. Now, I hope this is not too complicated because if it's not a unit disk, you can always use the Riemann mapping theorem to map into disk as used. So you recall that what we want for our eigenmatrix is that I want this mgx, right, to be roughly equal to x times gx. Yes.
Sorry, in the earlier example, I thought the eigenvalue was equal to pi I.
Yes.
But how can that be made x?
It doesn't. It's in the construction matrix. I have the freedom to do what I want. All I need is that I want x not to be too large for numerical reason. I don't want it. It could be x. It could be to the 2 pi x. It doesn't really matter.
Okay.
As long as it's one-to-one mapping. Because you see, as long as I can figure out x, I can figure out e to the 2 pi x. Or if I can figure out e to 2 pi x, I can take the log to figure out x. So these are equivalent essentially. Okay. But in order to present the original Prony's method, so e to the 2 pi x is more natural. Yeah. So the idea is the following: is that we want to design this matrix M such that M times Gx is approximate to x times Gx for any point x in the unit disk, because this is an open set. I claim that due to analyticity, I don't really need to check everything. But first is that, let me simplify this a little bit. Instead of considering the vector Gx, I consider the unit vector Gx hat. This is purely for numerical stability reasons, because the kernel itself might be very large at a certain point, it might be very small at other points, right? So therefore, if I just use its own magnitude to do numerical computation, it's not very stable, it's much easier to normalize it. This is especially the case when I have this exponential decay, right? Now, so therefore, what I want is I want the m times g hat is equal to x times g hat. Now, I claim that we don't need to check everywhere in the domain. I only need to check things on the boundary of this disk. So what I do is that I put a dense uniform grid, which I call AK, corresponding to these yellow points on the boundary of X. Okay. And I claim that we only enforce that M applied to G hat AK. So I only enforce with the parameter AK rather than arbitrary X. So maybe you see that this has 16 points. So I enforce this under these 16 points, G hat AK, M G hat AK is equal to AK times G hat AK. Now I will show you in the next slide why this is enough. Okay. Now, if you take a look at this formula, this essentially can be written in a matrix form. So you have this M apply this vector is equal to AK apply this vector. If I concatenate all these vectors together to this W matrix, and define this lambda to be the diagonal matrix containing these A values, then this formula for all the AKs together can be written in this form. Right? This is typically, this is when you learn from the eigenvalue decomposition, right? You write down the eigenvalue, eigenvector definition, and immediately you'll be able to write down this. Now it's easy because I want to look for M such that MW is approximating WA transpose, lambda. Then you use the tool which is called a pseudo inverse. Okay, it takes essentially the approximation of the inverse of W. So M is defined to be W lambda W pseudo inverse. That's the definition of my my eigenmatrix. And this matrix approximately satisfies this condition. Now, why do we only need to check on the boundary? Well, this is a very simple thing that you probably learned in the first few weeks of the complex variable class. Now, the reason is the following. Here, we have to use the fact that my kernel is self-analytic in X. So because my kernel is analytic in X, this function Gx is also analytic in X, right? Each entry is self-analytic in X. So therefore, so you can write the Gx as what? Usually Cauchy integral, right? As the integral 2 pi I on the boundary of domain Z minus X of Gx dx, right? And you put this M, hit this vector. Now, everything is analytic in X. And the next step I'm using the super exponential convergence of the trapezoid rule. If you have a curve, you have a periodic integral, what is the best way for you to do quadrature? You put equally spaced points. If the function is smooth, you have exponential convergence. So what I'm doing here is that I approximate this integral on the disk, on the boundary of the disk, with a discrete sum at this location AK. And the correct quadrature is given here, but you don't need to worry too much about it because it's going to be gone in a second. Now, at this location AK, I have MGAK is equal to what? AKGAK, right? Approximately. So that's also true. Now, I'm going to use the inverse of the trapezoid rule. Because this function is GAK is analytic in AK, but AK itself is also analytic in AK. So therefore, this is an analytic function. So therefore, this is a very smooth function. So therefore, trapezoid rule tells me that this is also true. Final step, Z times GZ itself is an analytic function. Apply the Cauchy integral theorem again. This becomes XGX. Okay. So therefore, this is just like combining with standard numerical trick and what you learn in complex variables. And this will tell you that you don't need to check everywhere point, enforce everything inside. You only need to enforce things at a very small grid on the boundary. Okay. Numerically, that's guaranteed to have exponential convergence. Okay, once we have that, we know that we have the first formula. M applied to G, xk is equal to xki. Okay, that's true. In fact, it's true for any x. So therefore, for the unknown location xk, that's also true, right? Now we do the same thing. We can define our u, the script u vector. This is bold u vector to be all my samples, uj, j between 1 and ns. Okay? And by using the same argument, the product of these m minus identity constant times identity matrix is going to kill each of the gk vector, gxk vectors. So therefore, it's going to kill its linear combination. So it's going to kill u. And if you write it down, you get again this multiplied with the coefficient of your polynomial. You can look for the null space. Once you have the null space, you write down the polynomial. Once you write down the polynomial, you find the root. The root is xk. To answer your question is that you see that I don't really need the e to the 2 pi xk, right? Xk will also be enough. Once I have the xk, I can solve the least square problem to figure out wk. And if you have noise, you can do a little bit post processing to improve the results. Okay, that's how I go. All right. Now, what happens if you have a general domain? Well, for the general domain, it's very simple. Because currently we have this space which is called X mapped to this space S, right? But if you have a general domain X, what do? We use the Riemann mapping theorem to map it to a domain called T, which is the unit disk, right? And this is my GSX. Now I compose these two maps because this map is analytic in X. Riemann mapping theorem tells me this is also analytic. So therefore, this map of G from S to T is also analytic, right? I can use this machinery to figure out what are the locations, what are the image of this inverse inverse analytic map in the T domain. Once I figure out in the T domain, I can push forward to figure out the location in the X domain. Okay, so that allows to do a general open set in the complex domain. So I think this is my phi, and this is my phi inverse. Now, what about the real case? So some of the examples I give you where X is real, right? So in the real case, let's start with the simplest example where X is the unity interval, not unit, but interval from -1 to 1. Now, what we want is that for every point X in this interval, we want to M apply to G hat. And remember, G hat is already the normalized G for the numerical stability reasons, is equal to X times G hat. Okay. Now, again, this uncountable number of X, we cannot enforce all of them. So what do? Well, another beautiful tool from numerical analysis is that we have Chebyshev grid. So we actually choose xk to be the root of the Chebyshev function. And these are corresponding to a grid which cluster toward the end, but get a little bit more space into the interior, right? This is a standard tool that we use in numerical analysis. So instead of enforce this for all the X, we only enforce this on the AK locations, which correspond to the Chebyshev. And once we have that, we can write by introducing this W matrix corresponding to these vectors at the Chebyshev grid. and this lambda corresponds to the diagonal at these championship locations, what we want to enforce becomes MW approximately equal W lambda. Again, we do pseudo inverse, we get M is equal to W lambda W pseudo inverse. Now again, why championship grid is enough? Well, again, you're using the analyticity, right? But here we use the complex analyticity early on, but here we use the real analyticity. So if you apply M to any GX using analyticity, you can actually interpolate this GX function using the found vectors at the championship grid with this DKX corresponding to my championship weights. Okay. Again, by linearity, M is going to hit on this G vector. But using the fact that at these AK locations, MGAK is equal to AKGAK, and I have this approximation. And finally, using the fact that this is also analytic, real analytic, championship is accurate, so therefore this is also equal to this function evaluated at the location X, so it's XGX. So here again, this is corresponding championship interpolation weights for the location X and associated with the grid point, with the championship point AK. Now, suppose, we don't have the -1 to 1 interval, what do we do? In general, if you have a general interval, or if you have an analytic arc, what we do is that we construct a smooth map, which map from -1 to 1 to X. And then we do the same thing, right? Consider this as my function. Try to figure out the location of my unknown deltas in this domain, and then we'll push forward to find out X case. Okay, it's the same as this picture. So if you want, instead of suppose you have a general arc, what we do is that we map this using this phi function, map to -1 to 1, and this is my T domain. And then this map G as T is self-analytic. I can figure out the location here, and then push forward, allow me to figure out the full location. Okay. All right. So this is the algorithm. Okay. So now let's just try to see how it performs numerically. And I will show you these 5 examples. So the first example is rational approximation. It's exactly this picture I showed you earlier. So X is a unit disk, and the kernel of the function is just 1 over S minus X. And now in this example, Sj is corresponding to a bunch of points randomly selected outside the disk within a ratio with radius between 1.2 and 2.2, and actually 40 points. So here, this picture needs a little explanation. So each of the picture, this circle corresponding to the boundary of X. And the top, I studied 2 cases. The first case is easy, the second case is hard. So in this case, you see that these 4 spikes actually inside the disk, and they're actually quite well separated from each other. So in this case, the information doesn't get mixed very easily. So therefore, it's an easy problem. On the other hand, in the bottom row, so you see that these 2 spikes are actually very close to each other with a very short distance. So therefore, it's much harder for an outside point to sense where the information comes from, right? The information can mix very easily. So that's a hard case. So this is top row and bottom row, easy and hard. Now, from left to right, we add noise, okay? So this is actually a harder case. The noise I add is roughly about 10 to minus 2 standard deviation. So it's quite a lot of noise for this U-pose problem. And this problem I added 10 to minus 3 noise, and this one I added 10 to minus 4 noise. Now I have to explain what are the different colors. So in each of the figure, you can see the points with 3 different colors. The blue one corresponding to the exact solutions. So you see here that the blue one, 1, 2, 3, 4. These are the 4 exact locations. These are what I want to recover. The green one is the result I get by doing this root finding. And so what I mean is that before post-processing, you remember I said that when there's noise, I want to do post-processing to my results. So you see that the green ones are before the post-processing. So for example, when they're separated, you see that even with very large noise, 10 to minus 2, even the green ones actually get very close to the true solution. So I'm pretty happy. But on the other hand, if you take a look at this case, the green one is actually quite a bit off. Okay? And in this case, the red one is also a bit off. So you see that when things get clustered, if your noise is large, it's actually much harder to detect. Now, what is the red one? Red one is the result. You take the green one as the initial guess, and you feed it into the final step of post-processing and to improve them. So that's the red one. Now, so you see that, starting from 10 to minus 3, and the results are quite nice because even the green one is actually very close to the blue one, my true solution. With a little bit of post-processing, you see the red post-process. So when you have 10 to minus 4 error, you see that in both cases, both the green one, which is before processing, and also the red one after post-processing, they exactly snap on the true solution. Okay, so which means that our algorithms actually can handle this case quite well. So this is the first example. The second example is this Max-Bar grid, the spectral density estimation. So again, so the band of my spectrum is from -1 to 1. So this is my parameter space, and the kernel is exactly the same. The Sj is corresponding to the so-called Max-Bar grid, which actually varies from. In fact, there's also a negative imaginary axis part, but I didn't draw it. It's from this number to this number. Okay, so where n is equal to 128. So you will see that actually corresponding to 256 different sampling locations on this imaginary axis, uniform. And now, even though this is uniform, but this uniform doesn't help you because the kernel itself is not uniform in this direction. So this is actually a very hard problem, which physicists care about. Now, this beta, which is corresponding inverse temperature, I set it to be 100, so the temperature is like 1 over 0.01. Now, here is this spike plot, which shows you that what is the location of the true energy gap and also what we recovered. So again, top row is easy. You see that these 4 deltas are well separated away from each other. The second row actually is hard because you see that there's 2 deltas which are very close to each other. Okay, so this is a hard case, this is the easy case. And again, I tried noise level 10 to minus 2, 10 to minus 3, and 10 to minus 4. And again, the blue one corresponding to the true solution. The green one corresponding to the solution I get before post-processing, and the red one is the one that after post-processing. And in all cases, you see that the green one actually already quite accurate even for the very large noise. It's not off by a lot, right? Here is off by a bit, here is also off by a bit. But once you run post-processing, it snaps right on top of the true solution. Accurate. Yes?
Can you explain again what the post-processing method is?
Oh, post-processing, yeah, let's go back. Post-processing is this. So after you get my spike location and spike weights, right? So you see that this is a 2 procedure. I find the location first and then find the weights. Once I find them, I treat them initial guess to do a local optimization. Oh, sorry, not here. So this is for the weights. It's actually go back a little bit more. It's right here. You take these point locations and the weights and feed them again to the overall optimization problem. So this is actually a non-convex optimization problem. But on the other hand, if I have a good initial guess, it's already in the local contraction basin. This will actually allow me to get to very accurate solutions. Yes.
Or are you just doing a gradient descent?
You can do gradient descent. If you don't like to calculate gradient, you can do derivative-free method. That's cool. Yes.
In your examples,
Yeah.
if you have some fixed weight,
Oh yeah, right. The weight is actually equal to 1 in this case. Yeah. So that's actually a simple case, but I think. But yeah, I tried different other ways, but if one weight is really tiny, then it's very hard to discover. But if all the weights are comparable, then qualitatively the results are the same. You see all the spikes are same height, so it's 1. So the next example is the Fourier inversion. So here I have the Fourier kernel, and the parameter space is from -1 to 1. And Sx are random points uniformly, random points chosen from -5 to 5. Okay, it's not uniform grid; it's randomly chosen. Okay, and I choose 128 points. I mean, we don't really need that many. I mean, for 4 spikes, we don't really need 128. I mean, 32, 64 also works, but I didn't optimize this number. So you see, again, this is an easy case because the 4 frequencies are actually well separated from each other. This is the hard case because the 2 frequencies are close to each other. Again, I tried 10 to minus 2, 10 to minus 3, and 10 to minus 4. And you see, again, the green ones actually was able to recover the location quite well. Right? In this case, it's a bit off. And this is already quite close. But after you do the post-processing, you see that in all the cases, red is almost indistinguishable from blue. So therefore, the blue true solution is the same as what I get after the post-processing. Okay. The next one. So this example is called Laplace inversion. So again, this picture shows you that I have 2 decaying modes, one decay rapidly and the other decay much more slowly. So the parameter I have, for example, the exponential decay rate is chosen from 0 to 2. I cannot choose this decay rate too fast because then otherwise you will immediately see no signal, right? So I have to choose this somehow within a reasonable range. And in order to map it from -1 to 1, I choose this simple map, just shift by 1. And the sample location is actually choosing from 0 to 10. Okay, and I use about 100 samples. And this picture shows the result. Again, this is actually a easy case because I have 4 spikes. These 4 spikes are try to separate away from each other. This is the harder case because the middle 2 spikes are actually very close to each other. This is a really hard problem because the Laplace transform, this exponential decay, lose signal very, very quickly. So if you have any noise, it's going to be a very severe problem. So here I use 10 to minus 5 noise. This is 10 to minus 6. This is 10 to minus 7. And you see that the methods, I wouldn't say the method is ideal, is great because, I mean, the problem is really too hard. But you see that when actually the noise level is not too large, 10 to minus 7, well, we can recover this quite accurately, right? For example, you see that there's 4 spikes. After post-processing, my red one is actually, in terms of location, is quite close to the blue one. And the magnitude is off by a bit, but it's roughly about within 20%. Okay? So the Laplace inversion is really very hard problem. So finally, I have this so-called sparse deconvolution problem. And the picture shows you have different bumps at different locations. I want to pick out the center of the bump and its weight. Again, the kernel is like a Cauchy type of kernel. And x is from -1 to 1. The sampling location is from -5 to 5. I have 100 of them. And this is the easy problem where the spikes are far away from each other. And this is a hard problem where the spikes are close. Again, here the noise is 10 to minus 2, 10 to minus 3, and 10 to minus 4. And you see that in both easy and hard case, when noise is below 10 to minus 3, then our reconstruction is very accurate. Okay. So the last one, I don't know why this, I should take back, but this one does have magnitude is off by a bit. Part of the reason because the kernel itself is very smooth. All right, so this is what I want to share with you. So this is thanks very much for your attention, and this is supported by NSF, and everything is in this. So again, I want to emphasize this is a very simple idea: is that you observe that for the Prony's method, the most important thing is the shifting matrix. At least one way to build it is the shifting matrix rather than this Hankel matrix. And then for general problem, you can construct the shifting matrix numerically. And this allows you to generalize what people have done hundreds of years ago for more general cases. Okay, thank you very much for your attention.